This problem has a little bit of everything. This is a partial fraction with a quadratic factor. Notice that this is a little bit different from what you saw in the video notes before today, where there was a repeated factor. That would have been if one of the factors was squared. In this case, we're talking about a quadratic factor. One of the factors has a quadratic in it and can't be factored anymore into linear factors. So when that's the case, the partial fraction decomposition that we're going to try and come up with, the a over x plus minus 1 plus b, all that, if the denominator is quadratic, then the numerator might not just be a constant, just a over x squared plus 2. It might actually be a linear numerator. So what we're going to do, remember, we forget about the integral for just a moment, and we try and figure out what this x squared minus 4 is. So x squared minus 4 over x squared plus 2 times x minus 1. We're saying that we want to break that up into the sum of two fractions. And remember, the logic behind this is if we wrote it as the sum of two fractions, we could integrate each fraction separately, and then we'd be able to add those two integrals together to find the overall integral of the entire fraction. What's different is, instead of just a over x squared plus 2, our numerator might be linear. So I'm going to write ax plus b. It doesn't matter what order I use the letters in here, those constants, the capital A, capital B. They're just some unknown constant I'm going to solve for. Call them whatever you want. And then for my next fraction, well, I need another letter, so I'm going to move along and call that a c over x minus 1. So we are going to try and solve this equation for a, b, and c. So we'll do the same thing we do with the other ones. We'll multiply by the denominator to cancel out all those denominators. And what we'll be left with after that is x squared minus 4 equals, for the first fraction here, we'll multiply the ax plus b times x minus 1, and then the x squared plus 2 over x squared plus 2 will cancel. And for the second fraction, it's c times x squared plus 2, and the x minus 1 over x minus 1 will cancel. Now our job is to find the a, b, and c, and we're going to use the same strategy we used for the simpler versions, where we'll just pick a value for x, plug in that value in a way that will make some of the constants disappear, and we'll just solve for whatever ones are left. So the first thing we're going to say is, if x equals 1, then this x minus 1 is going to be equal to 0, which means this whole thing will just zero out, and we'll be gone with our a's and our b's, so we'll only have a c left to solve for. And so that's what we'll do. If x equals 1, then our equation is 1 minus 4 equals 0, 0, 0, 0, 0, 0, 0, plus c times 1 squared plus 2. So negative 3 equals 3c, so c has to equal negative 1. What's nice about this is we can now start using that negative 1 if we need to help find a and b also. Okay. So then we're going to say, all right, we got rid of the a and the b together so that we could solve for c. Now we need to get rid of one of the other variables. The one that's going to work is, if you notice, there's an ax right here. So if we make that x into a 0, the ax will just be 0, and then there'll be no more a, and then we'll be able to solve for b. So that's our next strategy, is to let x equal 0, and then we would have 0 minus 4 equals a times 0, which I'll just ignore, plus b times 0 minus 1, so that's negative b, plus c, which we already know is negative 1, times 0 plus 2, which is negative 1 times 2, So negative 4 equals negative b minus 2. And so if we move some things around there, move the negative 2 over, and then change the signs, we can solve for that and say that b equals 2. So 2/3 of our constants are figured out. To find the next one, we've got a slight problem. We have no way of making the, because the last constant we need to solve for is the a, we've got no way of making this b disappear without making the a disappear also. So it's a little bit more complicated than just making one of the factors disappear. What we're going to do instead is just pick any other number. Pick an easy number. Unfortunately, we've already used the easy numbers, 0 and 1. But, just climb up the list. Let x equal 2, something that at least is easy to do the calculations with in our head. If x equals 2, then our equation would be 2 squared minus 4. Well, that's 0. That's nice. Equals a times 2. Remember, we don't know what a is, so we're still going to call that 2a. Plus b, but we just said that b is equal to 2, times 2 minus 1, which is just 1, plus c, which we already said before is negative 1, times 2 squared plus 2, which is 6. So 0 equals 2a, and the plus 2 minus 6 is minus 4. So add 4 to both sides and divide by 2. A is equal to 2. And so we have done the partial fraction decomposition. We now know how to rewrite our original integral, the integral of x squared minus 4, oh my god, I forgot a dx, over x squared plus 2 times x minus 1 is equal to the integral of putting all of our, I'm just going to rewrite this with my a, b, and c plugged in, 2x plus 2 over x squared plus 2 minus, because the c is minus 1, 1 over x minus 1. And what we can do now is integrate that. And the fun is just getting started, because there's a bunch more to do here. So the first thing I'm going to say is the last piece there, the minus 1 over x minus 1. Hopefully you see that and your immediate reaction is like, oh, that's a plain simple old x in the denominator. Very little fancy going on there. That's just going to be an ln. Great. But in order to integrate the other fraction, 2x plus 2 over x squared plus 2, first I need to separate the two integrals. But while I'm doing that, I'm going to say, well, 2x plus 2 over x squared plus 2, I don't have any method of solving that that's going to work. Unless I chop up that fraction into the sum of two smaller fractions. So what I'm really going to do is not chop this up into two separate integrals. I'm going to chop it up into 3. The integral of 2x over x squared plus 2 dx plus the integral of 2 over x squared plus 2 dx. And that was all about chopping up that numerator into two separate fractions, minus the integral of 1 over x minus 1 dx. And so now we've got 3 different integrals and 3 different methods of integrating them. You can pause the video real quick just to see if you can identify the 3 methods I'm going to use for each of these 3 integrals. Hopefully when you paused, the first thing you noticed on this first fraction was we have a denominator whose derivative is in the numerator. We like that. We're supposed to be looking for that first. That's u sub. Right there is u sub. Because if we say that x squared plus 2 is the u, the inside function, then we can say du is 2x dx. I don't even need to fix the coefficients here. Everything is perfect. I can just replace that with the integral of du, that's my 2x dx, over u. So I'll use the ln for that. That's great. The You know what I'm going to do is move the integrals around. I'm going to put the other easy one here first. And then I'm going to put the harder one on the side. The only reason I did that literally is because that way I have more space to work. So we've got two easy integrals now. We can integrate the du over u is the ln of the absolute value of u minus the integral of 1 over x minus 1 du is the ln of the absolute value of x minus 1. And then in order to work on the last one, we're going to say, all right, well, what does this look like? The integral of 2 over x squared minus plus 2 dx that I forgot. Well, what does that look like? We can't use u sub because the derivative of the denominator is not in the numerator. We're missing an x, so we can't do that. Integration by parts won't get us anywhere. There's no product that's really helpful here. But we see the quadratic in the denominator. So that is what we saw in our last lesson. You see that quadratic in the denominator there, or a quadratic in a radical. Either way, our first thought is, okay, well, I can think of that as a right triangle. And again, remember from our last class, our thought for creating the right triangle is which side is the biggest? Well, if x squared plus 2 are being added together, then it's the square root of the sum of those two squares that must be the hypotenuse. So the x and the 2 are the legs. It's really not 2, it's really a square root of 2. Because 2 is not a perfect square. And we can use that to identify, we can say that the sine of theta is equal to x over the square root of 2, so I'll put the square root of 2 over there. So dx is equal to root 2 times the cosine of theta d theta. And we're going to need to figure out a way to get this x squared plus 2 out of there. So I'm going to need to kind of worry about this in my triangle too. So I will say that that square root over root 2 is equal to the secant of theta. And we saw this in our last lesson during class, that what I can do here is if I want to figure out what x squared plus 2 is by itself without that pesky radical, I'll just square both sides. And then we can say that the x squared plus 2 by itself is equal to 2 times the secant squared of theta. And so I can do some substitutions here. Notice how this 2 is still around, haven't done anything to it. But the dx will be replaced by root 2 cosine theta d theta. And the x squared plus 2 will be replaced by 2 secant squared theta. And I just realized I had made a very silly mistake before, which I need to fix. You probably caught it while I was doing it. I used sine up here. That's silly. The x over root 2 is the tangent. That would be the tangent of theta, which means its derivative is not root 2 the cosine of theta. It's root 2 times the secant squared of theta, which is good because that means I can put that here. So everything will cancel out very nicely. So in my next row, I'm going to keep working on my antiderivative here. The ln of the absolute value of u, I might as well put my u back in. The ln of the absolute value of x squared plus 2 minus the ln of the absolute value of x minus 1 plus the indefinite integral. A lot of things cancel out. All that I'm left with here is root 2, which I might as well pull out, times d theta. And so we can integrate that. Something else that totally optional, if you notice it, you can do it. If not, not a big deal. But I've got the difference of two logs, which we learned way back. I can rewrite as the log of a quotient. It's not really any better, it's just condensed, so it takes up less space. And now I have to integrate that last piece, root 2 times theta plus c. And just like we saw in our last class, I am not satisfied with a theta in my answer if I'm trying to find an antiderivative in respect to x. So I'm going to have to look back to this original triangle and say, all right, the tangent of theta is equal to x over root 2, which means that theta by itself is equal to the arctangent of x over root 2. So I am going to have to put that in to my answer. Can't leave that theta in there. So I'm going to write this as the ln of the absolute value of x squared plus 2 over x minus 1 plus root 2 times the arctangent of x over root 2 plus c. And that is the answer to the original antiderivative we were looking for all along, the indefinite integral of x squared minus 4 over x squared plus 2 times x minus 1 in respect to x.